Good evening, everyone. The session will begin soon. As a gentle reminder, we ask you to kindly switch off your mobile phones to silent mode. This session will be recorded for informational, educational, and marketing purposes. The recording will be hosted on YouTube and our website for your viewing. A write-up and related materials may be made available alongside the recording. Do take note that the copyright for all the materials will belong to NTU. Welcome to the public lecture in the Dean's Distinguished Speaker Series. I'm Izera, a second-year accountancy student, and I'm honored to be your host for today. It is wonderful to see all of you here in person, and for those of you tuning in online from around the world. Thank you for being part of today's session. In tonight's session, we will explore how artificial intelligence is pushing the boundaries in decision-making, strategy, and financial modeling. Also, a special thanks to everyone who submitted their questions in advance. Our speaker and moderator will address as many as possible during the session today. Now, it is my privilege to invite Professor Byoung-Hyoun Hwang from the Division of Accounting for his opening remarks. Professor Zhang, please.
Good evening, everyone. I'm Professor Byoung-Hyoun Hwang from Division of Accounting, and it's my pleasure to welcome you to this evening's Dean's Distinguished Speaker Series. We are delighted to see so many of you here with us at Gaia Auditorium, as well as those joining us online. This is our fourth installment of our public lecture series, where we convene leading minds to examine pressing issues at the intersection of business, technology, and society. Tonight, we turn our attention to artificial intelligence, not just in the form of language models, but as powerful tools for economic insight. This session will explore a framework for optimizing and managing investment portfolios, uncovering return predictability across economic regimes, and providing fresh perspectives on corporate policy, risk, and strategy. We are honored to have Professor Byoung-Hyoun Hwang, Head of Division of Banking and Finance and the Provost Chair in Finance, as a moderator for tonight's session. Professor Hwang is a distinguished scholar in behavior and social finance, with research published in top-tier journals in finance and management. His work has also been featured in major media outlets such as the Wall Street Journal and Bloomberg. And he has delivered over 100 talks at academic institutions, conferences, and research groups worldwide. Without further ado, please join me in welcoming Professor Byoung-Hyoun Hwang to the stage.
Thank you, Professor Zhang, for this very kind introduction. Good evening, everyone. It is my great pleasure to welcome you to today's event and introduce our distinguished speaker, Professor Will Cong. Professor Cong holds the Rudd Family Endowed Chair in Management. He's a professor of finance at Cornell University. He's also the founding faculty director of the FinTech Initiative and the founder of the Digital Economy and Financial Technology Lab. I think these titles only begin to capture the breadth of his contributions to research, teaching, and thought leadership in financial economics. Professor Cong's work is, I think, pioneering in every sense of the word. He really has been at the forefront of fintech and integrating AI into finance. He's published widely in the top outlets in our field, like the Journal of Finance, Review of Financial Studies, and Management Science. He's given a lot of keynote addresses, and he's attracted extensive media coverage. His academic influence is matched by his policy and industry engagement. He has advised numerous organizations such as BlackRock, the Bank of Canada, the US Department of Justice, just to name a few. He holds a PhD in finance and a master's degree in stats from Stanford, undergrad degrees from Harvard. He also spent 4 years in Singapore at Hwa Chong, which is a pretty good school. When you hear all of this, you might perhaps believe that Professor Cong is all about finance, But that's actually not true. He's incredibly broad. I know this because Professor Cong and I used to be colleagues at Cornell University, and I still remember our walks from Sage to Statler, CTB, Mandible. We would talk about all kinds of stuff, and he would always have something very interesting to say. Like my son and we sometimes play this game, like, what kind of superpower would you like to have? And the one I would always like to have is this kind of time stop machine where you continue to operate, but the world around you freezes in time. Like for me, my primary motivation is that when we have to get up at 6 a.m., I just turn on that machine and sleep another 2 hours. But when I look at Professor Cong's CV, I kind of wonder sometimes whether you have one of those machines, because he actually published, he got his PhD actually only 11 years ago. And it's absolutely remarkable what you've been able to accomplish in those 11 years. It's truly impressive. So I'm sure you're all very eager to hear what he has to say. So please join me in giving a warm welcome to Professor Will Cong.
A very good evening, everyone. It's a great pleasure to be here with you this evening to share with you some of the work that my co-authors and I have been working on. And I'm very grateful for the very kind introduction and the invitation to begin with. As you might have noticed, the title changed a little bit. Instead of generative modeling beyond LLMs, I changed it to generative modeling using LLMs and beyond, because we are still utilizing LLMs, large language models, very extensively, and they are still helping us to understand many of the issues that social scientists care about. But at the same time, I do want to send an important message through today's sharing session that we should look beyond language models. There's a lot more that we can do taking the generative modeling framework to answer key questions in economics and finance. So I'll start with a general background. What is AI? You've been hearing generative AI, AI all the time. If you go back to the definition of AI, original definition back in the 1950s, it's basically technologies that allow machines to perform complex tasks, to solve problems, as if it possesses human intelligence. Then the question boils down to, what is human intelligence? Well, if you look at a recent definition from Stanford human-centered AI, it's the ability, again, to use suitable techniques to solve problems, to achieve goals. I want to emphasize goals here, right? In a very complex environment. So I didn't quite get the permission from many of my AI and data science colleagues, but I'm going to claim that modern AI is really about the following two themes, core themes. One is we're going from instruction-driven step-by-step optimization or step-by-step automation or prediction exercises, which our computers, car factories perform all the time, but we rarely associate that with intelligence, to end-to-end solution provision to very complex problems. And the way it's done is through enlarging the modeling space. If you talk about neural networks, deep learning, what are we doing? These are just a class of models, but they are much larger in terms of the modeling space they span relative to our conventional regressions or logic regression, so on and so forth. So that's one core theme of AI. Of course, over the past few years, generative AI is all the rage. What is so generative about generative AI? We're going to come to that. It doesn't have to be restricted to language models. So if I may highlight the few directions that AI has been heading into. One is we have larger and larger models, greater computation. I think that's discussed in the media all the time. And that's what our computer science colleagues have been working on and pushing the frontier. I don't think economists or financial economists have a particular edge over there, just because we don't have a lot of computation to start with. But that's a useful framework that we should think about. The second direction is big data. With bigger models, we need bigger data, which makes a lot of sense. Even without bigger models, with more digitization, we have more alternative or unstructured data that we have to analyze. That's fine. But the truth with finance, economics, social sciences is that unlike language models or languages or images, we don't have huge data sets. We can get satellite pictures, certain alternative data for finance, but overall we're still very constrained in terms of data. What I'm going to do is I'm going to hold these 2 dimensions fixed. I'm going to take that as given. And I'm not going to push too much along these 2 dimensions. But the next 3 bullet points will be more relevant. First, I already mentioned, right? What is modern AI? It's about goal-oriented solution searching within a large modeling space. So I'm going to highlight that. And in computer science, the de facto approach would be reinforcement learning. That's what's behind AlphaGo, self-driving machine translation, ChatGPT, and that's what RL stands for. I'm also going to touch upon the direction of generative modeling. And in fact, I'm going to argue it's actually very suitable for social science research, in addition to AlphaFold and all the science applications. And finally, we're seeing a lot of AI agents being deployed in the system or being used in experimentation to understand human behavior, human consumers, market survey, or simple economic experimentations. Along that dimension, we have to understand them as almost a new species. They are not always a perfect substitute for humans, and they interact with human agents in an interesting way. So that's an important direction of development, not restricted to economics or finance. But when we zoom in to think about applications of AI or machine learning in finance, what is the current status? We've seen a lot of applications of machine learning to predict asset returns. We try to introduce some structure in the models that we use. But most of the applications use supervised learning, training the algorithm through examples. And that's not what is core behind modern AI. Right? I just said it's about goal-oriented optimization, goal-oriented search. But that already allows us to handle big data, to think about interactions, to think about high dimensionality, which is great progress. We've also done a lot of textual analysis in accounting, in social science, going from simple bag of words to word to vec, to topic modeling, and nowadays to large language models. And that's great progress as well. But here I highly recommend the survey article by Jerry Holberg and Asaf Manila. They cover pretty much all that we need to know about textual analysis in finance. But again, I want to push this beyond textual analysis or language models. So what do? I'm going to go in the reverse order. I'll touch on point 5 first, point 4 with very quick remarks, and then I'm going to focus on point number 3, goal-oriented algorithms in a large modeling space, to give you a few more detailed examples. So starting with point number 5, how do we understand AI agents? I think there is an important direction that we can explore. That is the behavioral economics of AI. There is behavioral economics of humans, right? That's a very vibrant, thriving field. But AI agents, if we treat them as new species, different agents, they may not behave like us. It's an empirical question that we have to answer. Are they like us? Why conduct an experiment? Do they behave like humans? So what we did in a particular study shown here is we go through all the behavioral bias experiments, all the famous, well-known experiments in psychology, in experimental economics. And here is just one example, right? Talking about prospect theory, how people use reference point and have different sensitivity in the gain domain versus the loss domain. Again, my point is not to bug you with the details of the experiments, but I want to quickly show you some observations, right? When we do this type of experiments, what you see in the figure on the left, top left, would be 4 large families of large language models. And the circles represent how distant they are from human answers, human subject answers. So if you reach the outermost circle, that means the models, AI agents or large language models are behaving like humans. So we do see for preference-based questions, large language models behave a lot like humans in terms of the bias they create. But if we use the rational benchmark, which is the right circle, top right circle, what we observe is they are not very rational. And in fact, there are biases that are machine-like, not human-like, both deviating from the rational benchmark. And the lower figure shows you belief-based questions, calculating probabilities, forming expectations, so on and so forth. The LLMs are a lot more rational than humans. And there are reasons one can argue, right? When you use human feedback to train these models, they start to inherit the preference that humans have. But when it comes to belief-based questions, which involves a lot of statistics, the models become more rational and they are able to do the correct computation. That's just a flavor of the type of analysis we can do. This is restricted to individuals. Can you do this for a group of people? Can you do this in the setting where AI agents interact with human agents or human economic agents? I think those are all very exciting areas that we have little knowledge about, but represents a promising direction. Going back to bullet number 4, which you probably don't quite remember from the first slide, is generative modeling. Why is generative modeling very powerful? In the past, we cannot conduct data-driven analysis of counterfactual of the world. What do? Well, when there's a new policy comes out, let's say on inflation, we want to answer the question, how does that affect employment, for example? We have to build a theory model. We have to argue the parameters are deep so that when the environment or the policy changes, the human agents' reaction, their behavior don't change. They still behave according to these parameters. That's a very strong assumption. So what we can do now with large language models or AI agents or generative model is we can generate the counterfactual data and then take a data-driven approach. One example, which I put too much materials here, you probably wouldn't be able to read, I'll just describe it to you. Think about online lending after the introduction of large language models, right? Lending.com, Prosper.com, people will use these tools to file their application. If we look at historical data, we wouldn't be able to say, oh, what's the new funding rate? What's the misallocation of credit in this new environment? Because data is yet to be generated. But what we can do is we can take historical data. We can do something that borrowers would do using large language models. We can ask ChatGPT to improve the writing, to increase my chance of being funded. That generates borrower application data. Then you can train a potentially multimodal lending model for the lenders. They face this type of data. How would they respond to maximize their return on investment? So you get a counterfactual equilibrium response from the lenders. Then you go back to the borrowers, ask them, given this equilibrium response from the lenders, would you want to use large language model? Would you want to use it in a particular way? And if the answer is no, then this is not an equilibrium. If the answer is yes, this is one of the equilibria that in a counterfactual world that we can expect to happen, right? This type of analysis is not restricted to lending. You can analyze this for patenting innovation. You can think about the classic Lucas critique question going back to the employment rate. If you can generate job searchers' job application data and let the employers take a data-driven approach to the type of applications they are likely to face in a counterfactual world, you can do all this type of sandbox exercise for policy experimentation, essentially. And that is enabled by the generative modeling framework. Now, coming back to my main focus, I have to tell you what is the generative modeling framework and why is that tied to goal-oriented algorithms, right, in these large modeling spaces. In statistics, there is a distinction between discriminative models and generative models. For discriminative models, we typically have the X variables, the predictors of the features as given. We try to figure out the relationship of Y, right, given the X. In generative modeling framework, we have to think about how the X variables are generated, right? If I do reinforcement learning, say self-driving, I try to drive down this street versus the other street. I'm going to generate different data points to feed back to the model to train it. So X and Y are jointly created. Generative modeling framework is basically modeling the joint distribution. And you can do this in several ways. Here, at least big 4 families of generative models. Some of you have heard of diffusion model to help you to generate pictures or videos. That's what computer scientists and data scientists have led us in this aspect. And there are some additional models, but I want to highlight all these models are either unconditional generative models, meaning you model the XY joint distribution, or you have conditional generative models. You are given a Y. That's the condition. You want to figure out what X would generate that Y. So you want to create the X. Goal-oriented algorithms is actually a new form of generative model. And let me give you a very concrete example. Suppose I'm trying to form a portfolio. Traditionally, under discriminative framework, what I'm doing is I take the firm characteristics, right, book to market ratio, number of employees. All these predictors are my X variables. I try to predict return as the Y variable. Once I do this, I try to form portfolio as a next step, downstream task. It's clearly multi-step, it's not end-to-end. Sometimes that's not the ultimate goal, right? Suppose I'm managing a long-only portfolio, and I know one asset's expected return is super negative. It's not going to be part of my portfolio. I can't take short position. Do I want to spend my limited data observation or statistical power to estimate other, higher return moments of that particular asset, other properties of that asset? Well, if I care about asset pricing, yes. If I care about my portfolio, which is a long-only portfolio maximizing, let's say, cumulative return, it's irrelevant, right? So there are benefits to end-to-end rather than multi-step because the steps may not be fully aligned. That's discriminative framework, right? How would this look like in a generative framework? My Y variable is no longer the returns. My Y variable would be the portfolio management objective. It could be minimum variance subject to never losing 50% of the asset under management. It could be cumulative return, maximizing cumulative return, subject to taking a particular tax advantage. You can give me an arbitrary objective for portfolio management. That's the Y variable. I use that Y variable to think about how do I generate my strategy. So X variables will be the parameters of my portfolio strategy. X variable will be the portfolio weights, the combination of assets. And that's a very large space. I can take any combination, right? And the strategy space is also very large. So traditionally, if we do a full search, that's just not going to be very feasible. And that's why goal-oriented, clever search algorithms in the large modeling space will be very helpful. So I'm going to go to 3 particular examples, well, actually more than 3, depending on the time I have. Many of you have heard of hallucination. I do want to quickly highlight that hallucination and creativity are the 2 sides of the same coin. If you don't allow any creative attempts in coming up with a good solution to the complex problem we present, then it's not going to hallucinate, but you also don't get to explore potentially better solutions than what we have already known in history. But if you allow it to wander too freely, it's going to give nonsensical answers. So it's a balance. And there are various ways to deal with that. One approach we've taken is robust control, and I'll come to that in a little bit. So let me go to the first example, managing portfolio. We call it alpha portfolio. We actually started to work on this back in 2018, just 1 year after Google published the transformer paper in 2017. And so we do use transformer. I'll come to what transformer really is. But the more important point is we use reinforcement learning. So what is reinforcement learning? I have to say one word, right? That's one algorithm to search in a large modeling space. In the example of AlphaGo, we're not spelling out all the possible moves. We're going to try some moves, see how they work, try some nearby solutions. If it's not working, try some far away solutions. It's a trial and error, right? If you study economics, it will be multi-armed bandit problem. You're trading off exploiting what you already know versus exploring a little bit of the unknown. You're balancing the two. And that's exactly what reinforcement learning is. And that's how we learn as humans, right? When you teach a child to use a remote control, you can do supervised learning through examples. They press a button, you say, oh, that's the correct button, a wrong button. What if there's no supervision? The child just presses one button and see a presidential debate, which is really boring, and they switch to a cartoon channel. They say, oh, this is great, I'm going to press more in this area. Until eventually, through the feedback from the environment, they learn how to use TV control, right? So that's essentially what reinforcement learning is really doing. Now, applying this to portfolio management, this essentially represents pretty much the earliest non-text-based generative model in finance. So what do we do? Let me show you the picture. Maybe it's a little bit easier to see. We take an asset, say a publicly traded firm's time series of firm characteristics, such as trailing 12 months earnings growth, number of employees, trailing 12 months. Those are our time sequence inputs. We put them through a sequence representation extraction module, for which transformer is an example. Some of you have heard of long short-term memory models or recurrent neural nets. That's all fine. These are engineering details. The idea is there are time series models that extract information in the time series of your data and represent them in the abstract space using a vector. Here, that would be R1, R2, all the way through asset RL. That's essentially asset embedding. You're embedding an observable asset into some abstract space. And that space is going to tell you more about the time series properties of the asset. That's where computer scientists would have stopped. But if you do asset pricing, you know there's rich information in the cross-section of asset returns. Assets are related. The returns are related. So we also add a cross-asset attention network, CAN. And that's not too complicated. We just take whatever is in the machine translation, right? They apply it in the time series, take that structure, apply the attention network in the cross-section. Again, these are just statistical procedures to extract information about the interlinkage of assets, asset returns. Once we have a scalar representation of each asset, S1, S2, and all that, you can take long position in the high score assets, short position, basically selling short the low score assets to form your portfolio. So far, there's no economics. It's just statistical information extraction and representation. Economics comes in when you give me the economic objective, the goal. You tell me I want to maximize Sharpe ratio, monthly rebalance portfolio, auto sample. That's my goal. Once I have that goal, I can look at the portfolio formed. Is it giving me a high score for that goal? If it is, I'll search more in that parameter space. If it's not, I'm going to search away from that parameter space until I settle on a good solution in that large modeling space through trial and error. Right? That's a portfolio management example. How does it work empirically? Applying this to US equity data, again, data set is very standard in asset pricing or finance research. So we are not enlarging the model, the data set per se, right? We're just going to use a different algorithm, a generative modeling framework to form portfolios. And here is the auto-sample performance. If you look at the Sharpe ratio generated, it's consistently above 2. Sharpe ratio means the return scale by the volatility you have to face, right, for the portfolio. You hold on average an asset for 4 to 6 weeks, so it's not high-frequency trading at all. It's just monthly regular trading. And if you control for various risk factors, Pharma French 5-factor, Ho-Xie-Zhang 4-factor, the annualized alpha is still consistently above 13%, which is quite a high number. Of course, if you introduce trading costs, you add other economic constraints, the number is going to drop. But it's still very sizable compared to the traditional strategies we have, say factor investing strategies we have. We also test this on 5 additional years of data. And that's the benefit of not publishing the paper in 5 years. As you know, it takes a long time to publish in social science journals. We have 5 additional years of data. We test that. The performance drops a little bit, but it's still quite significant, both in economic magnitude and in statistical measures. So that's a portfolio example. Can I take this framework to corporate decision making? CEOs, CFOs making decisions. Can we think more about that? Well, it turns out that that's actually quite feasible as well. So here would be an application of the reinforcement learning heuristic search algorithm in enlarged modeling space in the corporate finance setting. And the basic idea, well, I have to provide a little bit background about corporate finance research. When we build models in corporate finance, we typically have 2 goals in mind, right? We want to understand the economic mechanisms. We want to understand causality. If I take this action, what happens? We also want to be particularly relevant. We want to explain firm outcomes. We want to predict firm outcomes. We want to give recommendations to firm managers on what type of actions they can take. Traditional approach using reduced, sparse, simple models, regressions, or certain causal identification does a great job explaining the economic mechanism. But it's typically low dimension. We're varying one action, right? Do I issue equity or not? How much do I issue? But in reality, CEOs, CFOs are making high-dimensional decisions. I need to decide whether I issue equity. Do I buy back a bond? Do I open a new factory? Do I fire some employees? Do I invest the fund raised in R&D or hold it as cash? We're making high-dimensional decisions dynamically. We're also getting feedback from the market. So there is some limitation in explaining or predicting empirically firm outcomes. Structural estimation, if you are into the academic research field, means I build a theory model as a world model of corporate finance. Everything is causal if you believe in the theory. But then that's a great idea, but we're searching within theoretically tractable models. So that's a restricted modeling space. What we want to do here is essentially a data-driven structural estimation. So anything that's consistent with data, with empirical observations, are permissible. I'm not going to restrict the modeling space too much. So it's a very large modeling space. How do we solve this problem then? We're really treating CEO, CFO decisions as high-dimensional stochastic control. Basically, you are taking dynamic actions to fine-tune your policy, right? To maximize some objective. Maybe it's share value. Maybe it's CEO compensation. It could also be ESG objectives. But you have to give me an economic objective. So here is how we do it. We use 2 modules with neural nets. One module describes the environment. You can view that as a sandbox, a counterfactual machine. I take this set of actions, it's going to give me what type of outcome that I'm likely to see based on historical actions. And the second module would be taking that environment as given. How do I optimize the managerial decision? So that is, again, a reinforcement learner module. I try some actions against that environment, see the feedback. I fine-tune my policy, see the feedback, until eventually I come up with a good, optimal, dynamic policy. this sounds too good to be true. Why can't we build this environment, right? Well, to do that, we have to add some robust control techniques. So the fear is that the environment module we built might overfit. And the data generating process going forward might be different under the new market environment and policy compared to how historical data were generated. So how do we deal with this type of concerns? Well, we built many environment modules. We train them. They all work well on the training data and all that. But once we move them to a new test sample, a data set that we haven't seen yet, if they give me very consistent predictions, I feel a bit more at ease. Using data and computation, I can do a good prediction of the environment evolution. But if they give me very diverse predictions, that means the model ambiguity is very high. So the model I trained probably overfitted or suffer from data distributional shift problems in different ways. That's why they go all over the place. I can't fully solve that problem. But what we can do is, once we see that, we say, well, let's not rely too much on the AI recommendation. I'm going to add some penalty to how we train the algorithm. So that way we can essentially introduce something similar to Sharpe ratio for managerial decision, right? On average, the actions, recommended actions, can say lead to a 3% increase. But there's a big dispersion. So once we consider the model uncertainty, model ambiguity, maybe that's not the best policy we should explore. That's the basic idea. How does this work in terms of predicting firm outcomes along various dimensions, such as changes in account payable, inventory changes? Out of sample, we can predict firm outcomes to over 30 or 40% R-square, and you can view that as how much variation that the model can explain, which is pretty high. Traditional corporate finance models in sample typically does 10% R-square, 10 to 12%. And if you take out here, when I say ignoring control information, what I mean is that the manager's action during that quarter or that month is not immediately known to the outsiders, right? So if we don't observe the managerial actions, how they manage the firm, along certain dimensions, the predictability goes down a lot. And that's actually not bad news. It tells us along what dimensions managerial action really mattered. Along what other dimensions, if you tell me the firm history, I can pretty much predict how the firm is going to evolve. Managerial actions don't matter that much. And from this, you can think about how I reanalyze managerial compensation, managerial skill. How do I contract? Right? Which firms are more manageable? Under what market environment? You can start to do all this type of analysis in this new framework. The module is going to provide you recommendations of the optimal policy once you give me the objective. Let's say maximizing, in this particular case, next quarter or next 2 years, either market cap or enterprise value. And compared to historical actions, they can improve the performance by as much as 10% or even higher. Now you can push back on this analysis. You can say, well, maybe the objective is not what the managers really cared about, right, in the data. So we can actually extend the framework to think about how we learn about managerial objectives. And that's an exercise I claim that traditionally we can't do. When we do reduced form analysis, we're just looking at one dimension of managerial actions, right? Or partial decision making. You can't use so-called revealed preference, meaning you look at the historical action, assuming that's optimal. You can't quite answer the question, what must be the CEO, CFO optimizing? Traditionally, we can't do that. Now with this framework, you can basically add a what is called a inverse reinforcement learning module, which allows you to figure out the optimal managerial policy. At the same time, the weights that the CEO, CFO must have put on different objectives at the same time. And if you are into statistics or machine learning field, you essentially solve a min-max problem divided into two optimization problems, and they form a generative adversarial network. So computer scientists and mathematicians have provided very good solution for us over there. So we can just tap into that. But that's getting too much into the technical side. Now let me switch gear a little bit. I talk about reinforcement learning as a heuristic search in a large modeling space. There are smaller models, more interpretable AI models that use regression or classification trees rather than deep learning framework. So here, why do I call it AI? Well, according to the art of war, human intelligence is also manifests in the fact that we divide complex problems and conquer the smaller, less complex problems. And that's exactly what tree-based models do. Tree-based models group observations into different leaf bins, right? That's how you grow a statistical tree. So that's what we are going to do. I'm just going to quickly talk about the exercise so that you have an idea. I wouldn't be able to get into the finer technical specifications. So let's go back to a typical finance problem. How do we form portfolios? We might do a double sort along market cap and book to market ratio, right? Value size double sort. We might do a univariate sort, just sorting along one characteristic of the assets. But why do we do double sort? Why do we use these two to double sort? It seems a bit ad hoc to generate test assets, to generate investment portfolios. So there is a larger security sorting space. Using the 60, 70 predictors, we can do all types of permutations. But to search through that security sorting space is very computationally expensive. It's not quite feasible. That's why using trees is one feasible way. Trees basically represent greedy search. And here is an illustration, right? Suppose I'm grouping various assets at the root level of the tree. And I use standard deviation of dollar volume. If I normalize the variable between -1 and 1, so 0.2 will be 60th percentile, right? Suppose that's the threshold I try. I split observations into two leaf portfolios. Now, if I care about investment, or if I care about using these portfolios to test my asset pricing model, I want the combination of the portfolios to have as high a Sharpe ratio as possible. Finance theory tells us that would make them most effective test assets. That's going to give us the highest Sharpe ratio performance once we form the portfolio. So I can look at these two leaf portfolios, see what Sharpe ratio they generate. I try a different split variable, different threshold. I compute the Sharpe ratio generated again. Whichever gives me the highest Sharpe ratio, I'm going to pick that split variable to grow the first step of my tree. Now for the second step of my tree, again, I can try a different variable to cluster observations. Now I have 3 leaf portfolios. I try which one gives me the highest Sharpe ratio performance. Whichever gives me the highest, I'm going to pick that as the second split criteria. When I think about the second split criteria, when I grow the tree, I don't go back to the first step and ask myself, oh, what if I change my first step? What happens? No, the first step is fixed. That's why the algorithm is greedy. It's not guaranteeing us a globally optimal performance. What it's giving us is really just, locally, at that step of growing my tree, it seems to be optimal for my objective. And again, what is my objective here? Well, if I care about generating this portfolio as test assets, my objective is to have high Sharpe ratio. But it could be a different objective. And that's why it's goal-oriented. You can give me a different economic goal. It could be, again, cumulative return for 12 months, subject to never losing 40% of AUM. You can use that economic goal to guide the growth of the tree. And it actually kills 2 birds with 1 stone. You optimize your economic objective. At the same time, typically when we use trees, right, they tend to overfit. And here's the basic intuition. We'll have more and more leaves of a tree model. You have less and less observations. And the noise start to come in. That's why tree models overfit. Typically, we deal with the problem by averaging many tree models. And instead, that's called a random forest, right? You do ensemble methods. You put many models together. But when you do that, you lose interpretability of the model. You can't explain to your client, how did I generate this portfolio? But now with this new panel tree framework, because you use economic objective, that accounts for all the data observations, the noise gets averaged out. So with a few single trees, you can explain the variation across a broad board of asset returns. So you also gain interpretability. That's helpful. And that's for generating portfolio, right? Again, it's going to look something like this when applied to US equity, right? The data would tell me, well, if I explain, oops. Sorry about that. Yes, okay. If I split along these variables, that's going to explain the returns the best, or that's going to give me the highest investment performance. I didn't specify which variable I split along by myself. It's not a human-driven or expertise-driven model. It's a data-driven model. But it's guided by an economic goal, your investment goal. You can do this, apply this to different settings. For example, I can ask the question, many of you have heard of factor models in asset pricing or even in other fields, right? You can ask the question, what factors price what assets under what market conditions? And we know that answer is non-trivial. Why? The factors pricing US equity are different from the factors pricing, let's say, Chinese A shares. The factors pricing bond markets are different from the factors pricing, forex markets. But how do we group the assets there? It's by country, by jurisdiction, by asset class. Can we have a data-driven way to figure out what assets naturally group together to be priced by a small collection of factors under what macroeconomic environment? That's something we can use trees to do. So in a way, traditionally we put a lot of stress on the right-hand side of the model, right? You have to pick the right factors. You have to figure out the correct coefficients. Now we are relieving some of the stress to the left-hand side. How do I group my observations so that I can have a heterogeneous model, right? Different factors describing the returns of different asset groups. How do I do this, right? If I use a goal-oriented tree-based clustering exercise, well, my goal would be, once I generate every cluster of assets and fit a factor model for asset pricing, I want their joint marginal likelihood to be the biggest. Basically, in layman terms, that would be, I want to maximize the probability in data to see these outcomes, these returns. That would be my objective. I use that objective to create these clusters. And that's where the generative modeling part comes in, right? I'm generating asset clusters in a data-driven way in order to figure out a better asset pricing model. And in fact, this is somewhat related to physics, right? Einstein has been, in the late years in his career and life, he was really after the theory of everything. But we do know quantum mechanics explains small-scale phenomena better, right? General relativity explains larger-scale things better, or high-speed phenomena better. So maybe different models can explain different groups of observations better. And here we have a similar idea. Maybe different factors explain different asset groups better. The key is, how do we figure out what assets should be grouped together? And if we do this, right, we can generate all these clusters priced by different factors. To give you a more concrete example, we do see a few factors that are very common. Market factor, size factor appear in every cluster. So no wonder they were introduced very early. They seem to be very robust throughout the development of asset pricing, right? There are also other factors, so-called factors. Once you do this grouping of assets, they disappear. So they are really just manifestations of interactions of asset characteristics rather than true common factors to explain co-movements and all that. Again, I'm getting a little bit more technical, but the idea is, well, there are certain asset groups that we can use factor to explain, but there are also asset groups that no factor can effectively explain what's going on. For some asset groups, we can explain as high as 24% variation in the returns for these assets. That's very high. Traditionally, with asset pricing models, we get 10, 12% with Van French models, so on and so forth, right, R squared. So that's one way to think about grouped heterogeneity. Certain asset groups would exhibit a property different from other asset groups, but the groups have to be formed in a data-driven way. And when we allow them to be formed in a data-driven way, we are enlarging the modeling space. Now, another exercise similar to this group heterogeneity idea. By the way, you've all worked with group heterogeneity if you conduct research in social science. When you cluster standard errors in a regression, you are thinking about grouped heterogeneity, right? The error distribution is different for different groups. That's why you cluster them. But that grouping of observations is very restricted. It's specified by the researcher, right? It's normally distributed. It's, I have 4 groups, or by industry, I clustered errors. Here will be a little bit more flexible group heterogeneity that we're trying to capture. Another application would be related to predictability. Not all asset returns are equally predictable. Traditionally, what we do is we attribute return predictability of an asset to the predictors we use, right? The X variables we use, or the model we have. But predictability could be a property of asset itself. So certain assets are just more predictable than other assets. Here I'm sorting on the left panel the time dimension and the market size. Different colors means different levels of predictability. Darker color means more predictable. You can already see different asset groups have different level of predictability. I can also sort along dollar volume and earning price ratio. Some groups are very predictable. Other groups have very low predictability in their returns. You can do this exercise in the time dimension. There are certain episodes, historical episodes, predicted by lagged quarterly macroeconomic variables such as unemployment, inflation rate, right? It's predictive because I use last quarters to predict what regime we are in next. But high S&P 500 dividend yield and high liquidity regimes, values, they predict changes in the predictability regime. Certain episodes are more predictable. And if you match that to the events we observe in the economy, right? Here, right after the financial crisis, 2008 crisis, predictability actually becomes quite a bit higher. And there are other events that you can analyze, right? COVID-19, for example, or certain global events that's going to alter the level of return predictability in asset markets. Why is this relevant in practice? Well, in fact, you can form trading strategies that's generating a excess return of over 1.3, 1.4% every month. Of course, I haven't accounted for trading costs, right? Once you add that, maybe this is halved, but it's still very sizable. Why would this happen, you might ask? Well, if everyone in the market is using a so-called homogeneous model, they think predictability is uniform across assets. Yet, once you use a heterogeneous model, predictabilities differ a lot. That means the mispricing is very high in that asset. That means information is being more slowly impounded into prices because traders all use a universal homogeneous model. Investors face this type of risk, so that commands a higher compensation. That's one potential rational explanation of why such strategies would earn a higher return. And you can form other type of trading strategies based on the level of predictability. One thing I have to clarify is, it's not a given that highly predictable assets with highly predictable returns have higher investment performance. That's not the case, right? Suppose I can predict with 100% accuracy one asset's return to be 0. There's no way for me to form a portfolio to make a profit on the return, right? So I think this is an empirical pattern that we observe. So just to wrap this up a little bit, we are talking about more core themes of modern AI. One of them is enlarging the modeling space and cleverly search for a good solution. Reinforcement learning, as you've seen in Alpha Portfolio or Alpha Manager, is a heuristic search in a large modeling space with deep learning or deep neural nets. Tree-based models are a greedy search in high-dimensional sorting or clustering modeling space. They each provide good solutions. The tree models only contain about 100 parameters. It's a lot more transparent. So in a way, if you are doing social science research, you can try larger models, deep learning models. You don't have to. If you incorporate some domain knowledge, right, to structure the type of search exercise, optimization exercise, you can do as well with smaller, more interpretable models as well. And I mentioned the other 2 dimensions earlier, so I wouldn't repeat myself. But I want to tie this to social science research a little bit. What's so special about business or social science research as compared to science? Well, we do know we are dealing with, in a way, more complex situations. Agents interact. I have no idea what objective you have, what you are optimizing. It's not like an atom has its own mind. They are trying to trick their transaction counterparties. No, there's a physical law governing that. But in societies, in business interactions, in a way, it's very hard to model. But all the agents are goal-driven. There's something we are optimizing. And it's just very natural to use goal-oriented algorithms in such a setting, right? To generate their behavior, to generate data, and then analyze the data. In terms of methods and approach, we also face interview data, survey data, pictures. We have multimodality. And that's what generative AI models have been very good at, right? You have different types of inputs. You can come up with an answer that's very reasonable and informative to answer some of these questions. And we also touch upon this idea briefly. In social science, we don't have a lot of data, historical data, right? We don't get to experiment a lot. But now with generative modeling framework, you can generate more data. And you can use the generated, simulated data to train your model to gain more insights into the economic questions we are after. And so far in economics, in social science, we've made very limited attempts because generative AI only appeared over the past few years. I think is a very fruitful, potentially fruitful field for many social scientists to explore and to further our understanding of all these disciplines. So with that, I'm going to end the presentation or talk. If you are interested in some of the specific papers and summaries of the research, there's a QR code with some summaries of research that's being displayed. Thank you.
Thank you, Professor Will. Please take a seat. No worries. Meanwhile, could I also invite Professor Hwang up onto stage? We will now move on to the discussion and Q&A segment, moderated by Professor Hwang. Professor Hwang, over to you.
Thank you so much for this talk. They asked quite a few questions. So if it's okay with you, maybe we spend the first 10, 15 minutes just going through. We cannot possibly go through all the questions they asked, but maybe through some of them. And then the remaining 5, 10 minutes, we just maybe open up the floor for people in the audience. So you talked quite a bit about the possible benefits of AI. But some people are wondering what are possible risks, downsides. I think some of them are worried about their jobs. But then I think they're asking more broadly about is this going to destabilize things?
That's actually a question that I've been thinking about for a long time. Having worked on information economics, I think an immediate simple answer would be, with more generative AI, at least information-wise, we might face a lot of misinformation. What if an influencer use some AI tool? They can basically modify the content of another authentic information source and generate something that's very entertaining, and that reaches out to a broad audience. But some of the audience members might have seen the original source of information. Do they treat this as independent news sources? How do they deal with the information? I think that becomes quite complicated. And we're already seeing that in the influencer economy or creator economy. But more importantly, and I think this is something computer scientists have thought about, is actually in finance, we've seen a few studies looking at something related to the idea of emergence, right? We have individual AI agents, the models we use. Looking at them in isolation, maybe we don't detect any issues. But when they act together, do they lead to a phenomenon or macro outcome that's undesirable? In financial market, there are already studies showing if you use some simple reinforcement learning agents for trading, at some point they start to collude. And that's not something we want to see in financial market, in real markets. So those type of phenomena are very hard to predict. So I think a lot more effort would be required to understand that. And pushing this even further, there is the concern of alignment, AI alignment. How do we make sure they serve the purpose, the goals of humans? I don't think there is a solution. Researchers from every field is trying to provide some answer to this question. I do think that's actually a very scary outcome that we might face if the AI agents are not aligned with our objectives. We might quickly lose control of these AI agents. One example I typically use is how we are agents in some way of genes, of our DNA. They have certain goals in mind, reproduction, right, propagation of the genes. But once the human agents become intelligent enough, become unruly to the genes, we may not always serve that purpose. So similarly, if AI agents reach that level, it could be potentially disastrous for humanity and for the society. So I know it sounds a bit like science fiction, but there's a possibility.
I mean, it sounds, because in medical research, what we do is when we think there's a treatment or possible drug, right? You have to go through all kinds of trials, examine possible side effects, and only if we're really sure that this is probably safe, we go for it. And in AI, it seems like we're just going to go, we just close our eyes and just go for it.
Right. There's definitely that camp where we are pushing for progress, the next version after the next version. which could be beneficial, but compared to the existential threat, I think it makes sense to think about AI safety. And in particular, I think Singapore is a great place to gather different camps, different thoughts, groups to discuss these issues.
I see. Oh, that's interesting. Here's one question that's a bit of a naughty question in a bit. So one person is asking, or feel that your presentation he felt was a bit more on the technical side, and is asking whether he or she really needs to know all this technical stuff in order to take advantage of AI, because he doesn't know how to use ChatGPT, but it just seems to work just fine.
Yeah.
What are your thoughts on that?
Yeah, no, that's a great question. If you are not under any pressure to publish your research and all that, probably you don't have to, get into the nitty-gritty of these details. If anything, I think the need has been reduced, right? Even for coding, we can use ChatGPT to code rather than code everything ourselves. I do think we actually don't need to know the technical details, but it's still helpful to have a high-level picture of what these algorithms are doing, what their potential functionalities are, what are the potential issues. And in a way, it's related to a question I get a lot, right? As students, what should we learn in the modern digital AI age? Of course, understanding some AI tools is helpful. Maybe ChatGPT is fine. It's not too difficult to utilize. But more generally, I think the ability to manage AI agents, to manage a set of AI tools is actually quite crucial. And that's very much tied to business schools, right? We do teach people how to manage an organization, manage a large team. Now maybe it's useful to teach people how to manage a mix of human agents and AI agents, or a mix of AI agents. And the reason is actually tied to my earlier concern. If we worry about AIs taking over, maybe we're not going to yield full control to AI agents. So we'll still need people to manage a set of AI agents to work together to complete certain tasks. So in that sense, learning the managerial skill in a surprising way becomes important again, rather than the technical skills. Yeah.
It's actually a good transition, because I think there's a lot of students online, which is great. There's also quite a few students here. And many of them are asking, if I'm very new to this topic and I want to learn more about it, what are some good starting points? Like, what do you tell your undergrads at Cornell?
That's a great question. I think various universities have been developing or revising the curricula in order to provide the best education for all the undergrads and students that we have. I actually don't have a good answer to this, or complete answer to this. A lot of the learning materials are available online, right? If you want to learn machine learning, you can go to Coursera. There are some basic courses. If you want to hear about Kapathi's, Google video talking about AI, that's a good source. There are certain blogs by OpenAI or by, there's also a newsletter called, I think it's called the AI Rundown or Rundown AI. They give you some periodic updates. That type of exposure and learning through osmosis is helpful. Of course, at some point, it would be better if schools develop more structured curriculum to help the students. And I was actually looking into the courses at NTU. I think there's one on AI and society, I think, for undergrad. Basically, some structured approach to education, AI education, it's a great start.
No, I think like coming from the US, I was surprised how forward-looking actually Singapore is with their education, and particularly here at NTU. Yeah, so we do
Absolutely.
actually try to offer a bunch of those courses.
Right.
Maybe just two more questions. So some are asking, so AI systems are often seen kind of as rational optimizers, but then the real people in the world, there's lots of crazy people out there, right? So it seems a bit hard to use AI to predict human behavior. Like, how do you behave or predict how a drunk person, where that person will walk next? That's very, very difficult. So is it actually able to do that? You alluded to something like that on your slide 4, right?
That's right.
Is it possible to do that? And if so, how does it actually do that?
Yeah. So in the example I was showing with the behavioral bias analysis of AI agents, we did see AIs don't always behave like humans. There are biases, but some of the biases are machine-like rather than human-like. I think the tools are still useful. For one, you can use these AI tools to study certain biases, to better identify human biases. That's helpful. And if you want to use the AI agents to produce human-like behavior, I think the training set, the training data we have would be very crucial. If we have certain structural disparities in the way we grant loans, we grant patents, maybe the training data would make the AI models also biased against certain, gender or race groups. But at the same time, I think we need to be careful. When we use AI agents, they themselves generate new biases. I don't think that's talked a lot about yet. So I think these are useful exercise to do. It's not directly answering the question, but I think that there is hope that we gain more understanding of both human behavioral biases or behavioral patterns and AI agents biases. And actually, if I may add to that, it's actually very hard to simulate the interactions of human beings or the real economy. That's where some discussion about the combination of AI and on-chain economy, right, Web3 space, is potentially interesting because when you are in a digital environment where most of the interactions are rule-based, they're driven by automated smart contracts, it's a little bit easier to simulate the interactions and the environment. Suppose I want to try a trading strategy. In the traditional financial market, I have to worry about, are the traders rational? Are they, doing the right thing? But if I trade digital assets or crypto assets on-chain, a lot of the transaction costs, price impact are well specified at decentralized exchange. So in that sense, it's interesting to apply AI in that environment. Of course, whether we move most of the financial assets on-chain is a separate question. Maybe that never happens. But just in terms of a clean environment to think about using AIs to simulate real interactions, that's actually a pretty good setting. Yeah.
How do we want to should I ask one or two more questions from or maybe I'll just ask one more question that was coming. So let's say I don't want to create a model from scratch. I want to use an off-the-shelf product like GPT or Gemini. And then some people were asking, they're mostly fed using data from, let's just say the West, right? But let's say I want to kind of then use that to simulate and then as a result find the best decision for here in Asia, let's say. How do I do that? Like, do I just do the prompt, assume you're in Asia? Or does it actually even work? Or do I just have to start everything from scratch and just feed it mostly data from Asia, like more from the local context?
So I think our computer science colleagues probably have done a lot more work along that dimension. Just speaking from economic perspective, we do know in finance research or economic research, we do have the issue of garbage in, garbage out. If the data quality is not very informative, we can't do too much. I'm not saying the Western data is of lower quality, but if you want to incorporate some I guess local culture or local specific responses. My view is that you have to use local data, and I've seen some apps. Trying to recall the name. There's one called Other Health, and also Masa Kane, I think, in Africa. One is about language models. You have to use local language to train the model, which makes sense. If you study classics, you have to use Asian language to train the model. But the health one is interesting because certain illness, certain symptoms are very localized. Seeing the same symptom within a particular group in one location might imply something different when we observe that in another location. So I think all these would point to how we can utilize local data to train the model. Of course, there's a challenge, right? What if we don't have enough local data to train the model? And that's where, again, generative model itself is very interesting. Can you simulate data that's more congruent with local culture or local practice? Can you simulate in the environment, right? The interactions, and use that data to in turn train the model. That seems a reasonable way to go if data is limited.
Yeah. Hi, thank you. That was a very engaging talk. Thank you so much. So my question is more in the finance domain. I'm a finance guy. So I'm wondering if we can back out or reverse engineer the implied objective function of a central banker or a portfolio manager by observing their actions and then compare with their actual stated mandates, like for a portfolio manager who has to invest a certain amount of portfolio in the ESG stocks, or a central banker who has a mandate to keep the inflation under check.
Right. Are they abiding by the mandate, or are they trying different?
Yeah, exactly.
Yeah. That's a great question. It's related to the corporate finance setting, right? We're trying to learn about the objectives. So the argument, at least what we tried, is a revealed preference argument, right? So if these are the potential candidates for the economic goal, economic objective of the decision makers, what combination of the objectives must they have in order to make their historical action optimal, right? Supposedly they are all rational and optimizing their decisions. So in this case, we would need a few candidate objectives. Maybe the mandate is a default objective. There are some other potential, empire building type of objective or some behavioral objective as candidates. At the same time, we also need to know the optimal action corresponding to each objective in order to do the decomposition, right? Let's suppose I bought 10 shares of Apple, I sell 2 shares of NVIDIA. Maybe one objective would say, buy 10 shares of Apple. The other objective might say, sell 1 share of NVIDIA. What ways I can do a decomposition, right? What ways I have on these objectives. But that's provided I know the optimal action. So with the corporate finance environment, firm environment, is we typically can't say this is the optimal action of the CEO, because the analysis we typically do is controlling for other actions. This is an optimal action. But in reality, they are making high-dimensional actions. So that becomes quite challenging. And this particular framework becomes more useful. Now, in the setting of central bank, I think we would need more data, because there's not a big cross-section. In the corporate setting, we have many firms in each economy, in each market. So that allows us to train some of the models. But with macro policy, with central bank decision-making, do we have enough cross-section, or do we observe long enough time series to fully train such a model is unclear. I'm not saying it's not feasible, because the models are not super large. So you don't need super large data set to train. But relative to corporate finance or asset pricing settings, just the amount of data available becomes more of an issue. But framework-wise, I think it's essentially revealed preference argument. Yeah. And that could be a good project to work on. I wish I have macro background, but I wasn't quite trained in that area.
Hi, just want to ask about your opinion from a policy and governance standpoint. Looking at how fast AI is developing, right? Do you think that the only way that policy and governance can catch up is through using AI to govern AI? Or if not, then what do you think is a possible solution given how fast things are developing right now? Right.
That's a great question, and I think many governments are thinking about or dealing with. In the US, which I think, at least right now, there is an episode that's relatively open to more innovation, unconstrained innovation in the tech sector. There are still big AI initiatives being formed where there are red teaming groups and stress testing the system, so on and so forth. I think that definitely requires some coordination. You have to get many players, researchers, practitioners, policymakers to come together. I think government has to lead that initiative. ChatGPT is now going to initiate that that particular coordination due to different incentives, right? As a private firm, will that fully resolve the problem? Do we have to try a gazillion different scenarios, right, to figure out what are the risks, so on and so forth? I think that's still a very open question. At this afternoon, with some of our computer science colleagues here, we did chat about how do we improve alignment, right? How do we make sure it's safe? Because these agents are very creative. We do allow them to be creative. So it's hard to write out or spell out all the possibilities. In economic jargon, we talk about incomplete contract. We can't spell out all the contingencies. And so maybe we can borrow some idea from how human societies are governed. When I take a Uber or Grab, right, we see a list of actions that we expect the driver to comply with. That's not a full contract. There are certain actions that we didn't mention. But we don't worry that too much, because if the driver takes a very crazy action, there's still a background law in the society that's going to penalize bodily harm and all these things. So accumulating certain cases over time is helpful, but AI is moving too fast. We took centuries to accumulate legal cases and all that, right? Another thing that's helpful is deterrence. Why death penalty is a very powerful deterrence, at least in some settings and countries. Do AIs feel the same? Right? If you tell an algorithm, if you do something that's unruly to humans, I'm going to shut down the algorithm. Are they fearful? Are they concerned? It's a little bit unclear, right? I haven't died yet, but I fear death. Why? Well, there's a long history of evolution, right? Those species, I'm just taking a more evolutionary view. The species that didn't fear death have already died, right? The ones that are more careful survived in a way. Do we have to have AI algorithms go through a similar process? Does that mean we need to quickly iterate AI generations? If anything becomes wrong, we shut it down. But how do we make sure that is passed down through their genes or memory to the next generation of models? I think these are all very open questions, but that takes a research effort and expertise from all fields, right? Legal fields, social science, humanities studies, and computer science, data science, which is a pressing issue that we need to think about before it gets too late. Yeah.
So probably better to join the private sector now. right? So you don't have to be the government to do all this.
No, it does take all these agencies to work together. Yep.
Thank you.
Thanks for the
Does
question.
anyone have maybe any last very quick question? Because we got to wrap it up, actually. All good? Oh, perfect then. Right on time.
Thank you, everybody, for your very thoughtful questions, and a special thank you to Professor Will and Professor Hwang for the very engaging discussion. So without further ado, we would like to take a moment to show our appreciation to our esteemed speaker, Professor Will. Could I please invite Professor Simba up to present the token of appreciation? Professor Will, please.
Okay. Thank you so much.
Professor Simba will now present the token of appreciation to Professor Will. Thank you, professors, for the informative sharing and the Q&A segment with many valuable takeaways. So if you've enjoyed today's session, do join us for the upcoming Summer School and Conference as part of NTU's AI and Business Forum on the 7th of July 2025, right here at Nanyang Business School. You can sign up through the QR code. To all our attendees, both in person and online, we hope you found tonight's discussion fruitful. Before you head off, we just have a small request to complete a short survey on today's session. So please scan the QR code. It would really help us out with the planning for the next event. And with that, we conclude tonight's session. A very big thank you to our professors Will Cong, Professor Byoung-Hyoun Hwang, and everyone who has made today's session possible. Have a great evening ahead. Until next time, thank you.